In an outdoor ice tank in the far northeast of China, a team of engineers slid a smooth metal shape into the water underneath a floating sheet of ice, towed it forward, and watched the ice break apart above it. The metal never touched the ice, not once. No bow, no hull, no ramming, no crushing weight from above, just a shape moving quietly through the water below, and a fracture opening across the surface, as though something invisible had leaned on it from underneath. And the idea did not come out of a shipyard. It came from watching killer whales, which break the ice under resting seals by swimming hard beneath it, and from researchers who decided that was worth taking seriously as engineering. If this work survives outside the tank, then every icebreaker on the planet, the ones with reinforced steel bows and nuclear reactors and tens of thousands of horsepower, is built on an assumption that may not have to be true. Stay with me, because by the end of this video, you will understand exactly how a moving object can shatter ice without touching it, and why the hardest part is not the physics at all. Take a second and think about how strange the icebreaker is as a machine. It is one of the only ships on Earth designed not to travel through water, but to destroy something. Everything else in naval architecture points toward efficiency. Slice the waves, cut the drag, save the fuel. The icebreaker does the opposite, deliberately blunt, deliberately heavy, deliberately wasteful, and for well over a century, nobody has found a better way to do the job, and the job just became a lot more valuable. 9 days ago, on the 15th of August, a Chinese shipping company called Sea Legend sent the container ship Dubai Tower out of Ningbo, Zhuan, opening what is being described as the first scheduled weekly container service ever run through the Arctic. They call it the China-Europe Arctic Express. 8 fixed sailings between now and the 3rd of October, using 7 vessels. Cargo from China to northern Europe in roughly 20 to 22 days, against the much longer haul through Suez, with the company claiming around half the carbon dioxide, mostly because the distance is simply shorter. That is a real change in how goods might move between Asia and Europe, but there is a detail underneath it that matters enormously here. The Northern Sea Route runs along Russia's Arctic coast, managed end-to-end by Rosatom, the Russian state nuclear company. The route is carved into 28 sections, and every ship needs permission for each. Rosatom issues the permits, runs the monitoring, and operates the nuclear icebreakers that escort ships when the ice gets thicker than a given hull is rated for. So the first scheduled container service through the Arctic depends structurally on somebody else's icebreakers. That is not a small thing to build a trade route on. And it explains, better than any research abstract could, why laboratories in China have spent years quietly working on ice. Now here is the part almost nobody thinks about. An icebreaker does not cut ice. It does not slice it, saw it, or drill it. It climbs. The bow of a real icebreaker is not sharp the way a normal ship's bow is. It is rounded and sloped, almost blunt, and that shape exists for one reason. When the ship drives forward into the edge of the ice, the slope converts the horizontal push of the engines into an upward push against the hull, and the bow rides up on top of the sheet. Then physics finishes the job. The full weight of the ship, thousands upon thousands of tons, presses down onto a plate of ice that no longer has water holding it up, and the ice fails in bending. That last word is the key to this whole video. Ice is enormously strong when you squeeze it and comparatively weak when you bend it. That asymmetry is the crack in the material's armor, and every icebreaker ever built is a very expensive machine for exploiting it. Everything else about the ship exists to make that trick survivable. The hull is heavily reinforced. The steel resists brittle fracture at extreme cold because ordinary structural steel goes glassy and cracks at those temperatures. Every underwater surface is sloped and curved with no flat vertical faces, so pressure from the surrounding ice gets redirected upward instead of inward, which stops the ice from crushing the ship instead of the other way around. And when the sheet is too thick to break in one run, the ship reverses and rams it. Back up, accelerate, strike, repeat, sometimes for hours. There is a second problem, and crews will tell you it is often worse. Breaking ice is not the same as clearing it. Broken flows jamming ahead of the bow slow a ship more than the intact sheet ever did. So the hull also has to push that debris down and around the vessel, away from the propellers, which are far more fragile than the hull and far more expensive to fix in the middle of nowhere. All of that costs an extraordinary amount of power. Russia's newest nuclear icebreakers carry 2 reactors feeding around 60 megawatts into the shafts. China's own Xualong-2, its first domestically built polar icebreaker, is more modest. Its diesel-electric plant produces a little over 20 megawatts, of which roughly 15 goes to 2 steerable azipod thrusters. And what does 15 megawatts of propulsion buy you? Continuous progress through ice about 1.5 meters thick, with snow on top, at 2 to 3 knots. Sit with that. 2 to 3 knots is walking pace. 15 megawatts, enough to run a small town, spent to move a ship slower than you stroll down a street. That is the true cost of contact. Every gram of that ice has to be broken by the ship's own mass, which means carrying the steel, the fuel, and sometimes the reactor required to have that mass and move it. Engineers have been patching around this for decades, not solving it, patching it. Low friction coatings, so the hull slides more easily once it is up on the sheet. Air bubbling systems that blow a curtain of bubbles along the hull to cut friction between steel and ice. Healing tanks that throw hundreds of tons of water from port to starboard in seconds, rocking the ship to work it loose and crack the ice around it. Double-acting hulls that let a vessel turn around and break ice going backwards, using the propeller wash to chew through. Every one of those is genuinely clever, and everyone accepts the same founding assumption. The ship touches the ice, and the ship's mass does the braking. All you get to do is make the contact slightly less punishing. So researchers asked a different question. What if the ship never touches the ice at all? That field has a name: non-contact icebreaking. And the branch Chinese researchers have pushed hardest is built on something called a flexural gravity wave. Here is the simple version. A sheet of floating sea ice is not a solid lid on the ocean. It is an elastic plate resting on a liquid, and it can bend. The water underneath can move. The two are coupled, which means anything that deforms the ice disturbs the water, and anything that disturbs the water pushes back up on the ice. What you get is a wave that is partly a flexing of the ice and partly a gravity wave in the water beneath. That is a flexural gravity wave. Here is why it matters. Waves like this have a critical speed, a particular velocity at which the coupled system responds most violently. Move a pressure source along at close to that speed, and the wave stops simply traveling and starts building on itself. In the standard description, the water essentially stops holding the ice up, and the sheet is left carrying the load on its own stiffness alone. The amplitude climbs sharply, and if the disturbance is strong enough, the ice fails in bending. The weak direction, the same weakness the 10,000-ton bow was exploiting, reached by a completely different road. This is known as the resonance method of ice destruction, and it is genuinely old. It came out of observations that ice sometimes broke under moving vehicles, under trains at crossings, under aircraft taking off from ice runways. The Russian researcher Viktor Kozin formalized it, and it has already been used above the ice with high-speed hovercraft in both Russia and Canada, because a hovercraft has almost no draft and never touches the sheet at all. That is the version from above. What Chinese researchers have been chasing is the one nobody has managed to turn into practical engineering: from below. Instead of driving a load across the top of the ice, you move a body through the water underneath it. The body pushes water ahead of and around itself, and that traveling pressure field presses upward against the underside of the sheet. Get the speed right, and you excite the same flexural gravity waves from beneath. The theory goes back to Kozin in 1967, who analyzed waves generated by a body moving under an ice sheet and introduced critical speed. But as recently as last year, the literature was still stating flatly that non-contact ice-breaking by a submerged body approaching the ice from below had not yet been applied in practical engineering. Which brings us to Harbin Engineering University. Harbin sits in China's frozen northeast, and its College of Shipbuilding Engineering has become one of the most productive centers in the world for this exact problem. Much of the work is led by Professor Baoyu Ni, who has sailed an Arctic voyage himself as an onboard scientist, and whose group has been working through the entire toolkit of non-contact icebreaking for years, often with Chalmers University of Technology in Sweden and the University of Lisbon. The experiment I described at the beginning comes from that group. In a study by Hao Tan, Linhua Sun, and Baoyu Ni, with their collaborators, published this year in the Journal of Fluids and Structures, a prolate spheroid, essentially a smooth, elongated egg shape, was towed beneath an ice sheet in outdoor ice tank experiments. The team built a new underwater towing rig to replace an older cable-driven setup, constraining the body's horizontal and vertical motion at the same time. According to the study, that rig made it possible for the first time to directly measure the hydrodynamic forces acting on a body moving beneath an ice sheet. That sounds like a technicality. It is not. Until you can measure the forces on the body itself, you are guessing at the energy budget of the whole method. You cannot say whether it is cheaper than a bow. What they found was that 3 variables jointly govern how far the ice deflects and how badly it is damaged: the speed of the body, its depth below the ice, and the thickness of the ice. Not one master dial, 3 interacting ones. They also reported that the drag and lift on the body vary non-monotonically with speed, meaning the forces do not simply climb as it goes faster, and that they behave distinctly differently from the same shape moving under open water or under a rigid wall. The ice, in other words, is not just a ceiling, it changes the hydrodynamics of whatever travels underneath it. And the team proposed a new dimensionless parameter, built from measured ice deflection and a characteristic length of the sheet, to sharpen the existing criteria for predicting when the ice actually fails. And this is where the story gets bigger than one shape in one tank. Flexural gravity waves are only one item on the menu. The same group and its collaborators have been attacking ice from several non-contact directions at once. There is bubble ice breaking. Release high-pressure gas from an airgun underwater beneath an ice plate, and a bubble forms extremely fast while the plate above it fails. Researchers filmed this with high-speed photography and found the airgun bubble takes a distinctive pear shape, unlike the round bubble from an electric spark. They recorded an initial shock wave, then a secondary one, then a pressure spike when the collapsing bubble fires a jet upward at the surface above it. Different conditions produce different damage patterns in the ice. There is water jet ice breaking, specifically cavitating jets. Push water through a venturi nozzle, a constriction that drops the local pressure, and you generate clouds of cavitation bubbles inside the jet itself. Those clouds grow, shrink, and collapse in cycles, and every collapse fires a microscopic high-speed jet at whatever surface it sits against. Researchers comparing the 2 modes found a conventional jet is better at starting the first damage, while the cavitating jet is better at keeping cracks running once they have begun. Later work found venturi structures and shear cavitation notably improved sustained icebreaking and framed the approach explicitly as an option for polar underwater vehicles. And there is laser icebreaking. Carbon dioxide lasers emit at a wavelength ice absorbs very strongly, making them an efficient surface heat source for melting through it rather than fracturing it. Published experiments on clear ice reported average melting rates of roughly 4 to 6 millimeters per second at 60 watts, with the rate scaling substantially as power rose from 20 watts. Notice what all 4 share. Each attacks the ice at a scale far smaller than a ship's bow. A collapsing bubble works across millimeters, a cavitation microjet across less, a laser heats a spot. Even the wave method, which acts over tens of meters, does its damage by exploiting a resonance rather than delivering raw force. The energy is not bigger, it is aimed. Quick question before we keep going. If a cargo ship could open its own path through Arctic ice without a nuclear escort leading the way, would that make you more comfortable with Arctic shipping, or less, given what heavier traffic up there would mean for the environment? Tell me in the comments. And if you enjoy this sort of thing, Real Engineering Explained honestly, subscribing does help this channel keep making it. Now, the honest part, the part most videos skip because it makes the story less exciting. None of this is close to replacing an icebreaker, and the researchers are the ones saying so. Start with scale. These are ice tank and laboratory experiments. The spheroid study's own conclusions list what still needs doing, and the first item is upgrading the towing system so it can actually reach critical and supercritical speeds. Read that again. The resonance effect the whole method depends on happens at and above critical speed, and the rig could not yet get there. The same conclusions note that the assessment of ice damage remains primarily qualitative and that tests with different body shapes are still needed to know whether their proposed failure criterion generalizes at all. Then there is the ice itself. Much of this work uses freshwater laboratory ice. Real sea ice is a different material, riddled with brine pockets, trapped air, grain boundaries, and pre-existing cracks, with properties that shift with temperature, salinity, and age. Researchers studying flawed ice found that internal defects redistribute stress and speed up cracking, which cuts both ways. It might make real ice easier to break than the pristine version. It also makes it much harder to predict. Then the geometry. Resonance depends on the body's speed relative to the properties of the system, including ice thickness, ice stiffness, and water depth. Those change constantly across an Arctic passage. A method tuned for one set of conditions may do almost nothing in the next. And then the awkward practical question. A submerged body moving fast enough to excite resonance under thick ice is not free. It needs power, propulsion, and something to carry it out there. You have not eliminated the machine, you have changed what it does. Which is why the realistic near-term picture is not a world without icebreakers. It is a world where these methods become auxiliary. Tools deployed from existing vessels to weaken ice ahead of a hull, clear a jam, free a stuck ship, or let an underwater vehicle open a hole and surface where it otherwise could not. That last one may be the real prize. Icebreakers have deep drafts, so there are shallow Arctic waters they simply cannot enter. A non-contact approach has no such limit. And here's the detail that puts all of it in perspective. While these laboratories work on breaking ice with waves and bubbles and light, China's State Shipbuilding Corporation's Design Institute has been promoting something close to the opposite. A nuclear-powered multi-role icebreaker, roughly 165 meters long, close to 30,000 tons, driven by a molten salt reactor with supercritical carbon dioxide power conversion, designed to break 2.5 meters of ice continuously while carrying containers and around 150 polar tourists. It received approval in principle from the Classification Society RINA last December. So the same country is pursuing both answers at once. The elegant one in an ice tank, where the researchers are still publishing lists of what they cannot yet measure. And the brute force one, 30,000 tons of it moving through design approval. That is not a contradiction. That is what engineering looks like when the timeline matters and the physics is not finished. There is still something worth noticing in the pattern. For more than a century, the answer to ice was more. More steel, more tonnage, more power, more reactor. The research coming out of Harbin asks a different question. Not how much force can we apply, but where exactly does this material want to fail, and what is the smallest amount of energy required to make it fail there? Ice is weak in bending, so bend it. Ice fractures from defects, so find the defects. Ice absorbs infrared at a specific wavelength, so use that wavelength. That is a shift from power to precision, and it is showing up across a lot of engineering right now, in fields with nothing to do with the Arctic. So no, the icebreakers are not going anywhere. The Arctic Express is running its schedule this season with Russian escorts, exactly as planned. What is changing is quieter. In an outdoor ice tank in Harbin, somebody towed a smooth metal shape under a sheet of ice, measured the forces on it properly for the first time, wrote down carefully everything they still did not know, and published it. That is usually what the beginning of something looks like. Not a launch event, a list of unsolved problems, written down clearly enough that the next team can pick them up. So here is the question I will leave you with. The icebreaker exists because we assumed that beating ice meant overwhelming it, and that assumption held so long that people stopped noticing it was an assumption at all. How many other machines around you are built on a brute force answer that works well enough that nobody has bothered to look for a smarter one? Let me know what comes to mind in the comments. And if you want to keep finding the engineering hidden inside ordinary things, subscribe, because that is exactly what we do here.